Welcome to BTEC Revision. In today's lesson, we're looking at simply supported beams. By the end, we will be able to recall the forces and structures in supporting beams and calculate the forces and distances in supporting beams. What are simply supported beams? Beams have been used for thousands of years. They have been used in engineering for building bridges, cars, airplanes. That's just to name a few examples. And we need to learn a few keywords in order to access this lesson. Firstly, we have concentrated load, which is a force acting on a specific point along the length of the beam. Secondly, we have the uniformly distributed load, UDL for short, and that's a force distributed over the length of the beam. For example, let's start by looking at concentrated load. Now, we know here is the beam in this diagram, and the weight is acting all along the beam. However, there is a force acting on a specific point at A and B. Therefore, it is considered to be a concentrated load. Let's look at the next mass. You can see this mass is acting on the length of the beam. Therefore, it is considered to be a uniformly distributed load because it's distributed over the length of the beam. We are going to consider this beam to be in equilibrium, which means that the forces and moments acting on this beam are balanced. Here we can see we have support A, which is supporting one side of the beam. And on the right, we have support B, which is supporting the right side of the beam in this case. Each of these supports are providing a reaction. So for A, we have a reaction force due to support A, and at B, we have a reaction force due to support B. And this is what is required in order for this bridge to be in equilibrium, because the forces going down must be equal to the forces going up. And if you remember our lesson on moments, we should be able to calculate these reaction forces using the principle of moments. As you can see here in this beam, it's not very well supported. So how can we further support the beam? We can use something called rollers, which provide a support reaction normal to the contact on the beam. So as you can see here, below support B, we have drawn the rollers. The key thing about this is that it only provides vertical support. And pins can be used to provide extra support in any direction, both horizontal and vertical. And they can be placed above support A or support B. Now let's look at an example. We're going to calculate the reaction force at support B. First, we're going to draw a free body diagram. Here we can see the beam can be drawn as a straight line. Next, we can draw the center of mass, which has a weight of 1000 newtons. It's important to note here the UDL can be treated as a point load. So therefore, we can draw the UDL going down. Now the question is, with how much force is it going to act? We can see that the UDL is 3 meters in length, and the values here is 10 newtons per meter. So that means for 3 meters, there's going to be 30 newtons of force. And we can write 30 newtons for the UDL. And the reaction force we can draw at the end, and the pivot on the left side. We calculate the reaction force. We would consider the pivot to be the opposite support. In this case, that's A. Using the principle of moments, we can say the total anticlockwise moment is equal to the total clockwise moments. Looking at which one is anticlockwise, that's going to be the reaction force due to B. So therefore, we can look at the lengths. That's 10 meters. So that's 10 times the reaction force due to B. And that's going to be equal to the clockwise moments, and that's 1000 newtons. And the distance between the 1000 newtons and support A is 5 meters. So that's times 5. And there's also another clockwise moment, which is 30 newtons, and there is an additional 2 meters of distance. So that's 7 in total. So that makes that 30 times 7. Now, simplifying this gives us 5,000 plus 210, which is equal to 5,210. And that's equal to 10 RB. So therefore, we can say that RB is equal to 5,210 divided by 10, which is equal to 521 newtons. Now pause the video here and attempt this exam question. Now, just like before, we are going to draw a free body diagram, and the pivot is going to be here at A. We have the reaction force, RB. We have the weight pulling this down, 500 newtons. And we have our UDL, so that's 3 newtons per meter, which has a length of 2 meters. So that's total force of 6 newtons. And that's all the forces. We can now add in the distances from the force to the pivot, perpendicular distances, and that's 7 meters. And for the next one, that's 1 meter, and the last one is 2 meters. Now we can write down our principle of moments. Total anti-clockwise moment is equal to the total clockwise moments. Now looking at which is clockwise and which is anti-clockwise, anti-clockwise is going to be the RB, which is having that direction. If we consider the pivot to be A, so we can say the distance 7 plus 1 plus 2 gives us 10, and the force is RB. So that's RB times 10 gives us 10 RB. And that's equal to the total clockwise moment. And there's going to be 2. So we have 500 going down, multiplied by the perpendicular distance of 7 meters. So that's 500 times 7. And we also have another plus 6 times a distance from the pivot gives that 7 plus 1, and that's 8. Calculating these values, we would get 3,548. Therefore, dividing both sides by 10, RB is equal to 354.8 newtons. And that's the end of the lesson. If you would like to boost your grades, visit us at btechrevision.com, where there's lots more quiz questions and resources available.